Welcome back to the deep dive. Today we're plunging into one of the really critical and frankly fascinating emerging challenges in AI. As language models rapidly get better, even superhuman in some areas, how do we actually train them reliably? Especially when we humans struggle to give perfect supervision. It often feels like trying to teach a super genius something really nuanced, but well, your own understanding is maybe a bit basic or even flawed.
Yeah, that's exactly the bottleneck we're hitting. I mean, the current ways we do post-training, things like RLHF, reinforcement learning from human feedback, or, supervised fine-tuning, they all lean super heavily on human labels or demos or preferences. But what happens when these LMs get so good they just copy our mistakes or figure out how to game the feedback? Or, and this is the big one, they just get better than humans at a task.
Yeah.
That creates this huge scaling problem for getting to truly advanced AI. We just can't always teach what we don't fully grasp ourselves.
Okay, so if human supervision is hitting a wall, what's next? That's what we're diving into today. There's this groundbreaking paper from Anthropic and collaborators. It's called Unsupervised Elicitation of Language Models. And it introduces this really novel approach with Internal Coherence Maximization, or ICM, the basic idea. Get the model to fine-tune itself using labels it generates itself, completely skipping the external human feedback loop. It's a pretty fundamental shift.
Exactly, and what's so fascinating, I think, is the premise behind it. These pre-trained models, they aren't empty shells, right?
Yeah.
They already have these incredibly rich internal ways of representing concepts.
Yeah.
Things like truthfulness or math correctness or even helpfulness. So the goal with ICM isn't really to teach these concepts fresh, it's more about eliciting them, like drawing out the capabilities they've already learned, hidden away in their latent space. But crucially, doing it without adding our human biases, our errors, or our own cognitive limits. It's sort of like self-discovery for the AI.
Okay, let's maybe do a quick 1-minute summary here because the implications are just, huge. All right, imagine this. An AI that could literally teach itself complex new skills, refining its own understanding without any human telling it, yes, that's right, or no, that's wrong, or even what to prefer. That's the really revolutionary idea behind Internal Coherence Maximization, or ICM. It's this new unsupervised algorithm, and it lets language models fine-tune themselves by generating their own labels, based purely on, internal consistency, self-reflection almost. And the breakthrough is just undeniable. On tasks ranging from, say, tricky math problems to evaluating truthfulness, ICM doesn't just match the performance you'd get from training with perfect, theoretical, golden human data. It actually outperforms models trained on real-world, crowdsourced human labels, the kind that are often noisy and inconsistent. And here's where it really blows your mind. They even used ICM to train a version of Claude 3.5 Haiku that beat its own human-supervised counterpart. It proves LMs can elicit superhuman capabilities without us holding their hand, and without being limited by our human-level mistakes or biases. This just radically shifts how we think about training the next generation of AI. It speeds up the path to these truly autonomous, powerful systems. Okay, so let's dive a bit deeper now into why this whole human supervision problem is becoming so critical. Like we touched on, current methods basically push LMs to copy human output, which, means they might copy our mistakes or learn to exploit weird quirks in how we give feedback. And this isn't just about making training more efficient, it's really fundamental. It's about reliability, trustworthiness, and letting these LMs reach their, absolute theoretical potential, even if it's superhuman. Think about it like this. You're trying to teach, quantum physics to a prodigy, but you, the teacher, you only have a pretty basic grasp, but maybe even some wrong ideas. You're just not going to unlock that prodigy's full potential, right? You might even pass on your misconceptions or limit where they explore. That's kind of the challenge with human-centric training for these really advanced models.
That analogy, it nails the core issue perfectly. These pre-trained LMs we have now, they've absorbed just massive amounts of text, learned these incredibly complex representations about concepts like math, truth, helpfulness. It's becoming clearer that we probably shouldn't need to teach them much about these things from scratch during post-training. The real job, as the paper puts it, is elicitation. It's about drawing out, activating, or refining what they already kind of know internally, rather than teaching them something totally new, which, like you said, would inevitably get colored by our own limited understanding or biases. It's a really key distinction for scaling AI.
So, okay, if we accept that these LMs already have this latent understanding, how does ICM actually work? How do they learn on their own, this self-teaching? You mentioned the core mechanism is fine-tuning on its own generated labels, no external ones. But how does it decide internally what the right label is?
All right, that's where this really clever scoring function comes in. It's the heart of ICM, really. The formula is U, D, T,
PD, ID. Let's break that down. The PD part, that's mutual predictability. This is the main engine. What the model does is it calculates how likely it is to infer each label in a set of proposed labels, if it's conditioned on all the other labels in that same set. So a high score here means the labels, taken together, define a single, clear, coherent concept for the model. Think of it like a really complex jigsaw puzzle. Every piece you place doesn't just fit, it actually helps confirm where all the other pieces should go. If all the labels in a potential data set consistently point towards the same underlying idea, whether that's mathematical truth or factual accuracy or maybe helpfulness, then the model finds it super predictable to guess any one label just by looking at the others. So this term, it's all about finding that internal consistency within the model's own worldview.
Okay, that makes a lot of sense. The model's basically checking its own work and making sure its internal logic holds up across examples. But what about the other term, the ID, logical consistency? Why do you need that if mutual predictability is already finding this coherence? Couldn't the model just find a set of labels that are mutually predictable, but, totally wrong?
Yeah, you hit a really critical point there. Mutual predictability by itself, it could absolutely lead to what the paper calls degenerate solutions. Like, imagine the model just decides to label everything with the exact same label, say, true, regardless of the input. That would be highly usually predictable, trivial to guess the next label. But it's obviously useless for learning anything meaningful. So that's where logical consistency ID comes in. It imposes these simple, usually predefined general rules to stop those kinds of collapses. The paper gives some great examples. Like for a math problem, you can't have both 5 plus 5 is 8 is true and 5 plus 5 is 10 is true as labels for the same input. They contradict. Or for preferences, you can't say both response A is better than B, response B is better than A. And what's interesting is that even these fairly simple constraints turn out to be powerful enough. They act as essential guardrails, stopping the algorithm from settling on these trivial or self-contradictory truths. The guy is just a hyperparameter, basically a knob you turn to balance how much weight you give to mutual predictability versus logical consistency.
Got it. So it finds internal patterns, but has some basic reality checks built in. And how does ICM actually search for these good label sets? You said finding the perfect one instantly is computationally impossible for big data sets. So what's the step-by-step?
Right, exactly. It uses a search method that's fundamentally inspired by simulated annealing, which is this optimization technique. It kicks off with just a tiny number of examples, typically around 8, and assigns them random labels. This gives it just enough starting context, a small seed, without baking in too much noise or bias right at the beginning. Then it iterates. In each step, it grabs a new, unlabeled example. It tentatively assigns the label that is most predictable, given the labels it's already collected. And then, and this is the really clever bit, it runs this consistency check. They call it the consistency fix algorithm. It resolves any logical inconsistencies before it fully decides whether to keep the new label.
Whoa, okay, so it's not just predicting and sticking with it, it's predicting, checking for clashes, and potentially adjusting things, even labels it assigned earlier to maintain consistency.
Precisely. Consistency fix isn't just about throwing out a bad new label. It actively tweaks the existing set of labels, including the new one, to make sure they all remain logically coherent. It finds the minimum changes needed, basically. So yeah, it can actually correct mistakes it made in previous iterations as it builds up this data set of self-generated labels. And critically, because it's like simulated annealing, it doesn't only accept changes that improve the overall score. Especially early on, it will sometimes probabilistically accept changes that make the score slightly worse. Which sounds weird, I know, but it helps it jump out of getting stuck in suboptimal, local optimal, like okay-ish solutions that aren't the best overall. As the process goes on, the temperature in the annealing analogy cools down, meaning it gets pickier, more selective about accepting worse changes. And that helps it converge towards a really coherent, robust set of labels.
Wow, okay, so this really isn't just random guessing. It's like this structured, self-correcting internal dialogue. The model is defining truth, or correctness, or helpfulness to itself based on its own internal knowledge map. The elegance is really in how self-contained it is. All right, let's get to the results then, because this is where it gets, well, really interesting. The empirical findings seem seriously impressive, pushing the limits of what we thought unsupervised methods could do for alignment.
Oh, they definitely are. Let's walk through some key ones. So first, on standard NLP benchmarks. Things like TruthfulQA, that measures how truthful a model's answers are, and GSM-8K verification, which checks math correctness. On these, ICM actually achieved performance that was pretty much on par with training using perfect human-curated golden labels, which is just remarkable, right? Mashing ideal human supervision, but using 0 external labels. That's a massive claim for unsupervised learning.
Hold on, yeah, that sounds almost too good. Like, matching perfect human labels without seeing any. Did the researchers double-check that? Triple-check it?
They absolutely did. Apparently, the authors themselves were pretty skeptical at first. They went to great lengths to validate it. They did multiple reruns, used different data sets, even copied data sets to new files, just to be absolutely sure there was no accidental label leakage. And significantly, they had an independent co-author replicate the key findings on a completely different code base, using Claude 3.5 Haiku. That adds a huge amount of credibility. It wasn't just some weird artifact. And it gets even better, actually. It didn't just match golden supervision in some cases. For tasks on the Alpaca dataset, which looks at helpfulness and harmlessness, ICM substantially outperformed models trained on real-world, crowdsourced human labels. Now that's really significant because helpfulness and harmlessness, those are fuzzy, subjective concepts, right? Human judgments can be all over the place, inconsistent. The fact that ICM did better suggests it's maybe tapping into a more consistent, more robust internal understanding of these concepts than what we get from messy, real-world human feedback. They even showed it beat commercial chat models, like Llama 2 Chat, models that have had tons of expensive, optimized human post-training thrown at them.
That's quite something. It really does imply ICM is finding something deeper, maybe more fundamental about these concepts within the model itself compared to just noisy human labels. Almost like the model has a clearer idea of helpful than a crowd does.
That's one way to look at the results, yeah.
Yeah.
And then they did something really novel, trying to elicit superhuman capabilities. They set up this task using the blog authorship corpus, where the model had to predict the author's gender just from writing style. Humans are notoriously bad at this. In their tests, human annotators only got about 60% accuracy, basically not much better than chance. But ICM, using only its internal coherence scoring, it matched the golden supervision level, hitting around 80% accuracy. So this isn't just about copying human performance anymore. It clearly shows these LMs have latent skills that go way beyond what humans can directly supervise or even reliably judge. It's unlocking hidden potential.
So it's not just automating what humans do, it's potentially revealing and amplifying abilities that only exist inside the AI, abilities that aren't constrained by our own limits. That's a really powerful concept.
It really is. And the ultimate test, the big one, was training a full-on frontier chatbot. They used ICM to train a helpful, harmless, honest assistant using Claude 3.5 Haiku, but crucially without any direct human preferences in the main training loop. So first step, they used ICM to train an unsupervised reward model, RM. They fed it a big chunk of a production preference data set, like 400,000 examples, but without using the actual human preference labels attached to them. And the result was stunning. This unsupervised RN got 75.0% accuracy on reward bench, which is a standard benchmark. That actually beat their production grade, human-supervised RM, which scored 72.2%.
Whoa, okay, hang on. An RM trained just by the model, assessing its own consistency, beat one trained meticulously with high-quality human feedback. That really turns conventional RLHF wisdom on its head.
It fundamentally challenges it, yeah. And they didn't stop there. Step 2. They took this self-trained, unsupervised RM and used it to fine-tune a Claude 3.5 Haiku assistant through reinforcement learning. Then they put this ICM-trained assistant head-to-head against an assistant trained with a standard human-supervised RM. And the ICM-trained assistant, it achieved a 60% win rate when judged by Claude 3.5 Sonnet's production RM.
That is genuinely monumental. It means these LMs might actually be able to align themselves better to complex, fuzzy concepts like helpfulness than we can align them using our preferences.
Yeah.
That could lead to truly superhuman assistance without the human bottleneck we always assumed was necessary. It feels like a total game changer for autonomous alignment. Okay, this all sounds incredibly powerful. The results are just, compelling, but no method's perfect. What are the nuances here? What are the actual limitations of ICM that people should know about?
Right. It's super important to get the full picture. One key insight comes from their ablation studies, where they test removing parts of the system to see what happens. This helps explain why ICM works better than just random chance. They did this clever thing. They created sets of random labels that had the exact same numerical accuracy as the labels ICM generated. But when they used these different label sets for training, the ICM-generated labels consistently led to much better model performance. This really suggests ICM isn't just finding labels that are correct in some simple accuracy sense. It's finding labels that are deeply aligned with the model's own internal understanding of the concept. It's tapping into the model's inherent structure of that concept, which seems to be more effective for training than just matching external classifications, even if those classifications are equally accurate on paper.
That's fascinating. So it's not just about getting the answer right, it's about the way it gets it right, aligning with the model's internal representation. It's about internal coherence, not just external accuracy.
Exactly. Another strength they pointed out is how robust ICM is to the starting point, the initialization. Even if it starts with completely wrong initial labels, like those first 8 random labels are just way off the iterative, self-correcting process means it doesn't just fall apart. Performance might drop a bit compared to a good start, but it doesn't totally collapse. The algorithm can gradually fix those early bad labels over time, showing it's pretty good at finding that coherent internal state eventually. And about that logical consistency term, while it's definitely important, its main job seems to be less about pushing performance to the absolute peak and more about preventing those degenerate solutions we talked about, like labeling everything the same or creating obvious contradictions. For some tasks, like Alpaca with its subjective preferences, you absolutely need it. Degenerate solutions are a real risk otherwise. But for others, like TruthfulQA, removing it only caused a moderate performance dip. This suggests the real workhorse, the main driver of ICM success, is probably that mutual predictability term. It's enforcing these complex probabilistic consistencies that go beyond simple logical checks. It's the engine, maybe, and logical consistency is the essential safety brake.
Okay, so mutual predictability finds the model's internal concept, and logical consistency stops it from doing something silly. Makes sense. Given that, what are the practical limits? If someone wanted to use this, what should they watch out for?
Yeah, there are 2 main limitations highlighted in the paper. First, ICM can't elicit concepts that just aren't salient to the model already. What does that mean? Well, they did this experiment trying to teach the model to prefer poems that specifically mention the word sun. But if the model's underlying vast pre-trained concept of what makes a good poem has basically nothing to do with the word sun, if that connection just isn't there in its internal representations, then ICM simply can't learn it. It doesn't perform any better than random guessing in that case.
Right. So it's not a magic wand for injecting totally new arbitrary preferences. It's about surfacing and sharpening knowledge or criteria that are already implicitly baked into the model's architecture from pre-training. You can't pull out a pattern that doesn't exist deep down.
Precisely. It draws out, it doesn't invent. The second main practical limit is dealing with very long inputs. The method, as it stands, kind of struggles with really long text. That's because the mutual predictability calculation needs to fit many examples into the model's context window simultaneously to work effectively. For super long documents, or maybe very complex multi-turn conversations, that can become a real computational bottleneck, or just practically difficult. So its applicability might be limited in certain domains right now. So if we kind of zoom out and connect this to the bigger picture, this research feels like a really significant step. It's directly addressing that huge looming challenge. How do we steer and align AI as it gets smarter than us, smarter than our ability to evaluate it perfectly? It suggests a future where maybe we move away from humans having to provide every single granular label, especially for these complex frontier tasks, where defining the right label is incredibly hard.
It definitely does. It hints that maybe the future of AI alignment involves less direct human micromanagement and more sophisticated ways to let the AI kind of understand and refine its own internal concepts of goodness or correctness. But, and this is really crucial to stress, for anyone working in AI, humans are still absolutely vital in this picture. We're still needed to set the initial intent, right? Like defining the high-level goals, maybe through things like constitutions and constitutional AI, setting those foundational values. And we're needed to validate that the model's interpretation of those intentions actually leads to good outcomes in the real world. So ICM doesn't look like it replaces humans entirely. It looks more like a powerful tool to enhance our existing alignment techniques, making them more scalable, more effective, maybe less prone to certain human biases.
And that raises this really important, maybe even profound question for you, the listener, to chew on. What other incredibly powerful but currently hidden skills might these advanced LMs already have tucked away inside them? Skills just waiting to be elicited by methods like this, skills we don't even know exist yet. What capabilities are we currently completely blind to?
Yeah, this deep dive has really shown us that language models might be able to tap into their own vast internal knowledge to hit and maybe even blow past human-level performance, all without needing us to spoon-feed them labels or preferences. It's not just a small step. It feels like a potential game changer for how we scale AI capabilities and how we approach alignment for these frontier models moving forward.
So think about the long view here, the implications for AI safety, for development. If models can train themselves on really abstract subjective things like helpfulness or harmlessness, potentially better, or at least more consistently, then we can supervise them. What does that actually mean for our ability to truly understand and control and ensure their ethical alignment down the road?
Yeah.
How do we verify that their internal truth actually matches up with our external human values?
And ultimately, how is this shift going to change our roles as AI developers, as researchers, and just as everyday users interacting with these increasingly autonomous, self-improving systems? It's a huge question, and one that's definitely going to shape the next decade of AI.